karma points for you. Okay, and then I guess that we can start.
49.
We're 49, still 1 minute. Yeah, I guess.
Yeah, okay, we're good.
I guess
We
we are.
got 50.
Yeah, sure. So, still congratulations for being here on Sunday morning. Still doing well. Perfect. We're gonna go for the fourth talk. So we have here Andrew and Jaylee, and they're gonna talk us about like software engineering practices in Rust specifically. So, applause for them, and let's go.
Hi, I'm Hoverbear or Anna, and this is my friend Jay or Busy Jay. As you can imagine, he's very busy. I'm going to talk the first half, he's going to talk the second half. We work at a company called PingApp, which makes distributed databases. We maintain TyKV, which is a CNCF project. It's a distributed transactional key value store. Those are some big words, doesn't matter. We operate at a really big scale. We were one of the first major Rust projects in production, and we've been in production for over 3 years. We're responsible for 15 petabytes of data at over 300 customers worldwide. As you can imagine, we do a lot of engineering. Some of our customers are the largest companies in China. We're used in commerce, where some of our customers have over 290 million users. In banks, where we offer really good SLAs with no data loss. And on ride-sharing platforms that are consuming over 30 terabytes of data every day. This is a very high-performance, safety-critical system, and we really like Rust here. It's perfect. So, how do we go from beginning with Rust to actually doing some proper engineering? Now, you might have been at the point where you've read the Rust book, you've published your first crate, you're pretty happy, but now you get the big questions. How do I share my work? How do I migrate to Rust 2018? How do I do all of these other things I don't really want to do because I just want to hack? And you're probably going like this guy over here. So we're going to go on a bit of a whirlwind tour. I'm not going to deep dive on anything. If you want, we can talk about it after, outside. So first, connecting and sharing your work. I've had the pleasure of helping organize quite a few of these conferences and events, or being at them. The Rust community has over 90 meetups worldwide and over six conferences. As you can see, there's some in Europe, Russia, and Asia, and a couple in the US, but they don't really matter. There's generally an event every few days, so most of them are really welcoming to newcomers, especially if you have a project or something interesting to talk about. So please do. We want more people in more speaker slots. Okay, next one. How do you get to Rust 2018 from Rust 2015? Because you probably didn't start your project in the last month. It's really easy, because it operates on the crate bound, not on some other bound like Python does. You can just use cargo fix, and it will do most of the work for you. The best part is, if you're on 2018, you don't really need to worry about people on 2015 because they can still use your stuff if they've used a recent compiler. It's a little bit different when we're talking about release level because we don't provide the same guarantees. As you may see, Travis lets you configure to test multiple versions. Please do so, and please test on nightly. It's very important. We want to know when things break. And tell people to actually look at your CI script to see which versions you support. Okay, designing your APIs. When you first make your API, you probably just go for the simplest possible, and that's good. Simple's best. But a lot of things when you're trying to move into real-world use, Rust has a lot of trade-offs. Nothing's a silver bullet. You're going to fight from complexity versus convenience, readable errors versus flexibility, and speed versus costs. There's not always a right answer. So, for example, if you just want to accept references to strings, and I want to emphasize, if you're actually cloning the string internally, take a string. Do not clone without the user knowing. It's really mean. They'll hate you. But if you're taking a string reference, you can go impl asref str. And then in your code, you can just go asref. This means you can pass a string reference, or something else. Anything that implements asref str. Similar with collections. Your first attempt, you might accept an iterator. And then you're going to try and write and pass a vec. And you're going to realize that doesn't work. And you're going to look like this guy. The proper way to do it, you can try this, using into iterator. And now you can pass a vector or an iterator. That's because iterators implement into iterator. What a surprise. Now, when you've been writing Rust, you've probably seen this error message when you called a function that returned a result. Now, you can actually make your own. If you've got something that needs to be used, you can put this must use attribute on your code. That's great, because now, when someone goes to use it incorrectly, they get the same error message and they go, damn it. So, if they consume it, it goes away. Great. Now, quite often you'll have functions that take optional arguments. Generally, it's best to use a builder, but that's not always a good solution for your problem. Remember, trade-offs. If you accept an into option U64 or into option T, you're going to find that when you call into in there, that you can get your option out. And this means you can call with the value or an option or your happy little none. This means your user doesn't have to worry about writing sum. This is quite handy. You can do similar with variadic arguments, which we don't have. But if you're okay with having some really ugly shit in your code, you can simulate it with tuples. I'm going to show you a couple slides on how this works. First, you define some structure, because you can't implement things for things you don't define. And then you do some from implementations on what you want to support being passed in. Then you can accept an into whatever. Now, all of these things over here, they work just fine. It's really ugly. So don't use it all the time, please. It's not for abuse. One cool trick that we found in the last little while with Rust 2018 is you can now actually destructure and take from arrays. This was much harder in Rust 2015, and this is thanks to non-lexical lifetimes. This makes designing APIs that take fixed size arrays much easier, and you can do some really cool optimizations around that. So this seems really harmless, and if you're a beginner, you might be going, what the hell's special about this? But if you've been writing Rust for a while, this might surprise you. Wish will actually be talking about this later on in his metrics talk at, I believe, 1. A lot of people ask us about how we deal with errors, and we're doing some really nasty things with errors, and we're trying to move to using the failure library because we found that the standard error trait's a little bit insufficient, and a lot of people agree. Why? Because you can't downcast the cause of an error. You also can't get back traces. That sucks. The failure crate allows you to have both of these things, and it's really well documented. It goes out of its way to describe 4 different ways of dealing with errors in your code. 3 of them I think are good ideas. You've got the prototyping way, where you just pass around some strings. You've got the lazy way, where you just have a normal error type. And if you're writing some really high reliability software, it describes this other way called the error kind method. The first 2, you can probably figure out how they work just from hearing about them. And this link will take you to the book, which will describe them all in excruciating detail for you. I'm going to give you a little bit of a demo of the error kind, just so you get an idea of what it is, and I don't have time for more. So, first, we just define this error. And it contains this context thing, which comes from failure. Now, it's going to hold an enum, which we define down here. This doesn't hold, this is not a fat enum, it's just labels. And they have these attributes, which give some display message. And you can see we have to derive fail on it. Okay, you've all looked at it long enough. I'm going to change the slide. Now we're going to implement fail for our error, and we have to define these 2 functions where we take a backtrace and a cause. Right now, we're just proxying to the inner, but you might do more in your implementation. You also have to implement display, but that's not a surprise to you. And then we implement some froms. As you can tell, from and into are just crazy useful. It's important that you implement both for the enum and the context, because this is important on this slide. Oh, the next slide, sorry. We also provide some way to get at that context. Now, we can call something that gives you an error, and you can actually add some context that's specific to your library. And the user will be able to downcast and get that original error and all of the context that comes along with it. This means if your user actually cares about that error, they can dig down really deep and figure out what's wrong. If they don't care, they can still just unwrap it and crash. That's fine. If they don't care, you don't have to care. You don't need context, though. You can just use the enum. That's where we have those to from implementations. Okay, now let's talk about fuzzing. And I know you all like fuzzy things. I did not bring any fuzzy crabs for you. I'm sorry. I'm actually talking about the programming technique. Now, fuzzing doesn't replace your unit tests, but it does complement them because it finds out if you've forgotten tests or you didn't know about them because you weren't that smart. But please note, when you're implementing fuzzing, it shouldn't be part of your normal CI test runs when a new contributor makes a PR. That's mean, because if you get a failure, which they don't always happen, that poor contributor is very confused. So Travis lets you define the determinant event type. If it's a cron job, which you can make them, they're not hard, you can detect it. And that's when you should run your fuzzing. That way, every night or every morning when you wake up, you get a nice failure report saying how bad your code is. So fuzzing is a way to randomly explore the state space of your code. This means that you're not always going to run over the entire space. And this is a good thing, because if you're running, say, over a U64 state space, this could take forever to find one edge case. Fuzzing is only going to run a few thousand every time you run it. So it's a great way to find bugs eventually. And as you get more and more complex with your fuzzing, you're going to have a bigger and bigger state space. So you might think, it's no problem to run through a U32, and I agree, but a U64 is a lot bigger than a U32. We recommend that you explore prop test, which is kind of the newest one out. We're actually not using it yet, but it's a really great crate, and we've been playing with it, and we'd like to adopt it. It's from the quick check family of fuzzers. So essentially, the way you use them is you define some properties that get fuzzed over. It supports this idea of minimization. So when you're fuzzing over, say, a string, and it finds one that doesn't work, that's really long and crazy, it will go through a whole bunch more iterations to find the most minimal example it can, so that you're only testing very simple examples that break things. It also remembers regressions for you and keeps testing them to make sure you fixed it. So you can't be lazy, because we all like to be lazy, and tools that keep us honest are good. The way you define how to fuzz over things is quite a bit different in prop test compared to the other quick check family things. You actually define these strategies, which you can customize quite closely. I think it's a really good alternative to libfuzzer or AFL or quick check itself. You might have different opinions. That's great. I support that. I like opinions. Here's a little bit of a demo on how prop test works. This is the most basic one I could think of, and it's actually part of their documentation because it's the most basic one you can think of. We define some add trait or add function, and then we use this macro called prop test. And we define some ranges. You can see A in 0 to 1,000, B in 0 to 1,000. This means the fuzzer can pick any numbers between 0 and 1,000 for both A and B, try to add them together, and make some assertions. So when I run this, and I run cargo tests, it's going to run a whole bunch of them, and this state space is actually quite small. So it will probably only take me maybe 5 or 10 fuzz runs to get through the whole state space. As you can tell, though, this code has no problems. It's very simple. But if we were exploring all of the I-32 state space, I might have some problems because there's such a thing as overflow. But you're probably like, yeah, I don't really care about testing over U32s. I use a whole bunch of complex types. So what about like a key value? So a non-simple type that holds 2 byte arrays. You can go and you can implement a function which returns this strategy thing. And here on that tuple, you can see I have these regexes. And I can define these regexes to be whatever regex I want. And there's various other things such as ranges I can use for this. Then I call prop map, and I can use it to map to this new structure I defined. So this function will actually return to me an arbitrary kv value with some vectors, 2 vectors, with random garbage in them. Now, when I write my prop test, I can say kv in this arbitrary function, and it will go and get out random ones a whole bunch. This is great. As you can guess, though, the state space on this is gigantic. So I could probably run this 1,000,000 times and still have new outputs. So it doesn't explore the whole state space. It's not a silver bullet. Okay, Jay.
Okay, thank you, Anna. Anna just introduced some methods that help you to find bugs. And actually, it's quite easy to find out that an application doesn't work because it might panic or it will report errors. But to reasoning the bug usually can be hard because bugs can be unpredictable. It may be reproduced, it may not. And usually you will need more information to reasoning a bugs. I have been into some situations that I add some print and rerun it again and over this procedure over and over again. So it also needs logs. So you might think that I wish that time can just tip back so that I can collect as much as information that I need. And fortunately, there's a tool that can do this for you. It's RR. And it's a tool produced by the Mozilla, just as the awesome Rust. And it can record the failure once and debug the recording deterministically. And you can set breakpoints and watch points and execute it and reverse execute it. The command to use this tool is quite simple. Just RR recall, and once you find failure, then just replay. I will show you an example about how to use RR to debug a Rust program. And let me do it. Okay. I implement a simple program that just simulate a situation that has race condition. A fun fact is that Rust, when you write code in safe Rust, it's guaranteed that there is no data race, but race condition is unavoidable. And so we have an account. Account has name and the data directory. When you initialize an account, it will write data to the it will write its remaining money to the data directory. So sensitive. And you can query the remaining, and you can also set the remaining. And what we are going to do is the transfer. Transfer will first check if the source account have enough money. If it's not, it will return false. If it does, it will set the remaining about to the source and the target. As you can see, this program is just written for the just written as an example. So the logic is quite simple. And we can try to run this code. What a surprise, it failed immediately. But as you can see, we are not, okay. Usually we are not that so lucky. But turns out it's a good day today. I thought it's Sunday, right? Yeah, okay. Sunday. Yeah, Sunday seems a good day. The point is, once we find out that it's hard to reproduce the bug, it always passes, then how can we do it? How can we solve the problem? When using RR, due to the uncertainty of the network, I'm not going to run the RR in live. So I'll just show you some pictures to show how it works. The command you can see is I use RR to record a program with a H flag. H flag means that enable the chaos mode to the RR. It means that because RR actually will emulate a single core machine. So it will try to switch to other threads when there is some like 6 cores or some instrument count is reached. So the chaos mode is that just switch it whenever you can, so that we can reproduce the bugs very easily. As you can see that there is 78 in the end. That means I tried 78 times to reproduce this bug. And finally, I reproduce the bug. Then I can replay it to see what's happening. And just type R replay, you can see it shows up an interface that is very similar to GDB. Actually, RR use GDB in the hook. So when you replay the failure, it will pause at the very beginning. So when you type C means continue. It will just reproduce the bug we just record. So it panicked. It panicked at line 73, which is here. Anna is expected to have no money, but it has 20. So let's check out the transfer function. It turns out that the value set here is 20. So we can add a breakpoint to that line. That is, I add a conditional breakpoint. If the remaining minus amount is equal to 20, then stop it. And I use a special command here, is reverse continue. Because the program is panic, and we need to reverse it to the very point it just at the very point error happens. So after reverse continue, we see that thread 2 hit the breakpoint, and we just enter an empty command, which is repeat last command, just reverse continue. And it shows that there's 2 threads, different threads hit the same breakpoint. That means that's the very place race condition happening. That's how we use RR. As we just said that it emulates a single core machine. So if you are debugging if you're debugging a threaded application, it will have some decrease in performance. And the second limitation is it only works on Linux. Of course, it shouldn't be a problem at all. Okay. And so if you use RR to debug an application and you find out bugs, so and you believe that you fix it, but how to prove it? Usually we should write a test case to check it will never fail again, and to prevent is bringing back accidentally in the future. But stable test case can be hard. Of course, if you are lucky enough, it will be easy. Yeah, Sunday. So to stabilize the bug we just said, we may need to we need a special schedule policy to the threads. But unfortunately, we can't control this. It depends on the operating system. So how can we do it? We write a crate to do these things in name fail. It's free implemented in Rust, and this thing is inspired by the FreeBSD's fail points. What is fail points? Fail points are co-instrumentations that allow errors and other behavior to be injected dynamically at runtime. That means you can just use some use this library to make some threads like pause or sleep or yell whenever you want to simulate some failures like IO failure or syscall failure or anything else. And this is the GitHub URL. Welcome to start. And so let's see how to define fail points. There are three methods to define fail points. The first one is pretty simple. Just define a fail point using some unique name. And generally, when application run into the fail point, it will just emit the fail points, just like as if it's never defined. And the second one, there is a closure here, and I will talk about it later because it's used in a very unique case. And the third way is that we add a condition in the middle place. And the condition means that the fail point will only be triggered if the condition is true. So like if you run some tests concurrently, you can just make the fail point taken effect if the test is the specific you want to run. So you have defined a fail point. Then how can you configure the actions about the fail points? You can do it either via the environment variables, or you can just using the interface, API interface, just using the API. And it's quite simple. Just a pair of the name and their actions. Actions are defined in the format like this. There can be many actions, and only when the first action is not triggered, then the second action will be triggered. And every action is defined as P and count and task and arguments. P means that the probability that the action is triggered, and the count means that the max times the task will be executed. And currently, the supported tasks include this many. And I think the task name express themselves well. The only two needs to explain here is the delay and the sleep. Delay means that you can just pause the thread for the given seconds. And delay will spin the thread. It's a busy waiting. So let's take a look to the example about a fail point configuration. This means that the fail point has 20% probability to print a line still alive, and have 80% probability to just panic. And if it prints still alive, it will print as many as 3 times. And let's see how to stable the race condition we just described here. And we can see that I define a fail point. Oh my God. Slow update here. Because we know that the race condition is that the line 39 fetch remaining can be mutated before line 44. So actually, we should hold the lock in the whole function, but it's not. So we put a fail point here, and we add a configuration to make it sleep 100 milliseconds. So that in general, if there's no bugs in the kernel, threads will all block at this point, so that the stale read will be always hold. So we can run a test to see how it happened. I think something turns out wrong. Are we in the same direction?
Yeah. I don't have auto.
Oh, yeah. It's not my computer, so.
Yeah, sure. Blame the computer.
Yeah. Okay. Okay, what a day. So it works. Yeah, and so no matter how many times I try, it always panic. And this is what we want. We use fail point to make a test stable. So when we fix the transfer, it should be not panic again. But how to fix it is beyond this talk. So how does fail point work under the hood? Actually, it will maintain a global registry that map the fail point to its configuration. So every time the fail point is executed, it will query if there is any configuration for the fail point. If it is, it will execute the configuration. If not, it will just ignore. So you may wonder that if I define so many fail points in my source code, it may affect the performance of the application. It's true. So we offer a feature gate. We offer a feature guard that can make you disable all the fail points at combine time. So it's also one of the Rust philosophy. Just pay for what you use.
Yeah, so it seems we both timed ourselves out to be about 20 minutes, and we were both about 12 minutes. So thank you very much. We hope to see what you can build with some of these tips and tools. We're hiring distributed systems engineers. You can email me if you want a job. We really like remote people. We really like open source. We like to read research papers. We write Rust, Go, and C++. We hire anyone. We don't really care what you look like or how you identify. We like creativity, passion, and teamwork. But we have some time for questions. We have a whole 10 minutes. So if you have questions, please ask them. If you have comments, we can talk in the hall.
Transforms the code itself to see if the tests are covered by the tests are covering this kind of small errors, like changing the sign of an number, changing the direction of a comparison, things like that. Have you tested this kind of tools?
So the question was, there's some tools that exist that will actually mutate the code to see how robust your code is. That sounds really cool. I haven't actually encountered any for Rust. Have you? Okay, okay.
So I don't know if that exists for Rust.
I think. Oh, I think that sounds really cool, and I really want to try that now. So thank you. More questions?
So is it easy to somehow automate all the best practices you mentioned
So the question is it easy to automate some of these practices that we talked about using tools? Clippy will get you quite far. As I kind of discussed at the beginning, a lot of these are trade-offs. For example, if you're using some of the into tricks, you should try and minimize their surface so that they're only existing in the public API, because there is a compile time cost associated with them, and some of them do have a small runtime cost. So you do need to be aware if you're just throwing these everywhere, you're going to be paying for it. So a lot of these work best when you limit them only to public API. So I think a lot of tools might not do that. Definitely, I highly recommend you run Clippy on every build, though.
So for property testing, okay, it sounds very good, but the practical problem for most people is that how can you define those properties in a way that don't replicate the implementation? So was it hard? Are you actually using property-based testing, and was it hard to
So in TypeKV itself, we're currently using libfuzzer, which does not provide the same level of abstractions and tooling. So we have to do a lot of implementation to get it work properly. It's very useful in tools like databases, though, because when you're storing arbitrary strings and byte arrays, you need to be very careful you're not mutating them. Certainly, that you only get so much mileage out of fuzzers, though. There are other tools that you might want to explore when you're doing multi-threaded programming, such as Namazu, which will go and chaotically change how some of the threads are scheduled to help you find bugs in logic instead of just in properties. So the question is, are we aware of anything that reads contracts and helps us define properties automatically? Unfortunately, Rust does not have anything like HOR notation, similar to what you might find in ADA. So it's kind of hard to make assumptions about what the contracts are. I have seen some libraries trying to add things like contracts to functions. But most of them aren't really at the stage where I think they're kind of usable in production. That's certainly something that would be very useful to a lot of people. So if anyone's interested in implementing that, please do and tell me about it. So the question is, how do we choose the language we use on projects? Do you want to tackle this one?
Because we are writing TypeKV. Actually, we are in a more big project. It's named TypeDB. For TypeKV is the underlying storage for the TypeDB, and we want it to be more deterministic. For example, if actually TypeDB is written in Go. But if we use Go in TypeKV, it has the G-state problem, and its compilation its performance is not as good as Rust. And also because the storage is the fundamental of the database, so we want it to be safe and fast, and that's why we choose Rust to build TypeKV. Yes.
Yeah, I think Rust, the way the drop semantics works, is extremely useful when you need predictable performance, because you always kind of get really reliable function call runs.
If we were to change Rust in order to change the outcome of the decisions you go for the top level of TIDB, what would have to be changed in order to make it the winner, I guess?
So the question is, what would make it so that we would choose Rust for writing TidyB, the thing on top of us, instead of Go? I think we can both agree it's easier to hire Go engineers than Rust engineers right now, particularly in the distributed systems space, because a lot of Go engineers are out there slinging distributed systems code, and not a lot of Rust people are writing distributed systems.
And I would say that, although I don't want to admit it, but Go is really flexible than Rust, because you don't meet too much compilation errors in Go. So you can get things done very quickly. And in the circle layer, there is many functions and many other queries that you need to keep compatible with my circle. So use Go will be a more appropriate choice in this case.
We got time for maybe 2 more questions.
I really like this talk, so that's one. And the second, do you have more resources along these lines?
I would be very happy to chat with you and just give you a huge list, because like we work on this stuff all day and it's our favorite thing in the world. Certainly there's lots of great blogs out there. You can look at Nick Cameron's blog, Without Boats' blog, Aaron Turon's blog. They all talk about a lot of tools that are coming out, and they try and highlight some really cool things. But definitely, I think the Rust blogging ecosystem is really, really vibrant. Matthias actually runs a great blog. He just presented. And you can I find out most of the cool tech we find from blogs. And certainly, there's a lot of effort right now to make Rust things in research papers. As you may be aware, there's a Rust Belt project that's trying to formalize Rust and things like that. And they're discovering a lot of cool stuff you can do. So certainly, I think one of the most beautiful things about Rust is the really heavy research bend on it.
Your experience with the failed points, does it cause maintainability problems in the code? Because in the end, you have lots of failed points not at all about your code.
So the question is, does adding a lot of fail points make it hard to maintain your testing suite?
Yes, it does. So actually, we use fail points in production. And in Target, we execute all the fail point tests in sequence. So there's no races in this situation, but we are planning a feature to fail point is that supports like context-aware fail points, so that every fail point is bound to specific test cases, so they can run concurrently. So I think in this case, there will be no more headache about too much fail points. And I think this feature will come before the release of 1.0 of fails. Okay.
So we're at 43 minutes, so we should probably stop. It's been a real pleasure, and we can definitely continue the conversation outside if you want. Thank you.